Hi there everybody, welcome to another video in Math 1332, section 11.2, permutations. Before we go to permutation, I just want to define the use of factorial. So for any natural numbers n, natural numbers is start from 1, 2, 3, all the counting numbers start from 1. So n factorial is determined to be n times n minus 1 times n minus 2, all the way back to 1. So very simple. If we say 5 factorial would mean the product from 5 times 4 times 3 times 2 and times 1, and that is 60. Right, I'm sorry. 120. 5 times 4, 20 times 3, yeah, 120, sorry. Right. And on the calculator, if we want factorial, on this calculator, hit math, go to probability, option number 4, right? But before that, we have to hit 5, and then that 120, right? So, right, and then because with that we can say 6 factorial is 6, 5, 4, 3, 2, 1. But notice that we already have this, which is as 5 factorial. So you can write 6 factorial as 6 times 5 factorial. Right? Anyway, multiply all of that. 5 factorial is 120 times 6, that's 720. Right. Very simple. Now, there's a reason that it is convenient to use the exclamation point as factorial. As you see, we go from 6 all the way back to 1. We can stop at any number and then we put the exclamation point. Case in point, a factorial, if I want to, I can say start from 8, 7, and if I feel like it, don't want to write anymore, I say 6. But we know how it goes. Just put an exclamation point there, right? So we just go from 8, 7, and then from 6, we know the rest how it goes. 6, 5, 4, 3, 2, 1, right? So in that case, we just have 8 times 7 times 6 factorial. We already have 6 factorial, which is 720. Now just times 7 times 8. Yeah. So the nice expression of factorial is we can start from that, reduce by 1, and then whenever we don't want to write anymore, just put an exclamation point, and we know it has to be a product from that number back to 1. Right. Next we have this 12 factorial. If we write out 12 times 11 times 10, and because 9, 8, but I just want to stop here. The reason I stop at 10 factorial because we do have 10 factorial at the bottom. That gives us 12 times 11, which is 132. Right. Next, n plus 2 over n factorial. N plus 2, if we start from that, we have to go one number less than it, one less than it, and then so on. But I'm just going to stop at n factorial. And then here we have n factorial. Cancel those. Right, so that's what we have. Right, next we go to actually define a permutation. So an arrangement of n distinct objects. So we have n distinct objects, focus on the n objects in a specific order called a permutation of the objects. The number of permutation of n objects using all of the objects are n factorial. Right, we don't really need this. But the arrangement of n objects, let's say we choose a number from 0 to 9, and we only use R of those objects. Let's say we only pick 3 numbers from those. that is called a permutation, and each arrangement is called a permutation, and it is written as NPR, and the formula is n factorial over n minus r factorial. The formula here is nice. We don't even need the formula. Right, let's go over some example first, and we'll see. The formula is nice if we use the calculator, but if we use by hand, probably don't need to. Right, here, an example. You need to arrange 6 of your favorite books along a small shelf. So the order, you can put the first book and then the second book, and then you can scramble them. And each time you scramble, you have a different arrangement. Right, how many different ways you can arrange the books? Assume the order of the books make a difference. Right, so the most important in the permutation is order does matter. Orders matter for permutation. Right, so order of the books makes a difference. So let's just write this. So we have 6 different slots, and you're going to put 6 books into those slots. The first one, you can choose any of those 6 books. Then you have 5 books left for the second slot. 4, 3, 2, 1, and multiplication rule. Multiply all of that. Always write 6 factorial, which is 720. Right. So like I said, we don't even need any formula. But if we do, we're going to arrange 6 books. We choose into 6 position. Right. So we have 6 books, and then we choose 3 of them. And order does matter. And the formula is, let's just write here. So we just have 6 factorial over 6 minus 6. So that's 6 factorial over 0 factorial. Oh, we have that on the first page, but we also define 0 factorial to be 1. Right, of course 1 factorial is also 1. So that is 6 factorial, 720, 0 factorial is 1. So that's just 720. Right, so I arrange 6 books. We use 6 books and put in 6 position. Now if we only choose 6 books and we put in on, we choose 3 of them to put on the shelf, that's how much we have. 6 and 5 times 4. Right, so keep that in mind. Order does matter. Right, next. There are 7 horses in a race and a large jackpot for anyone who can pick the finishing order for all 7 exactly. How difficult is that for the number of possible order they can finish in? So if we want to do that without the permutation, just say there's 7 slots. 7 slots. 7 for the first one, 6 for the next one, 5, 4, 3, 2, and 1. Right, because we have 7 horses, and we pick all 7, order all 7 exactly. Of course, in this case, order does matter, because if order doesn't matter, you have 7 horses. There's only one option to choose all of them, right? So order here does matter. So have, for the first part, you can choose any of those 7. The second spot, you only have 6 left. So you have 6, then 5, 4, 3, 2, 1. All of that together, 7. 7 math probability option 4 50 40. Right, next. We're going to choose 7 horse and then put them in 7 spot. And so, of course, we can use the same thing, but here we can just say If we use the permutation in the calculator, hit the 7 first, go to math, probability, NPR, and we do 7 out of 7. That also 50/40. Alright, or just 7 factorial, either way, right? Now things will get more interesting. Now, how many different ways can the pledge a class with 20 members? So we have 20 to choose from. And we have a president, vice president, and the Greek consul. So there are three different positions. And order does matter. And no pledge can hold 2 offices. Order does matter. Because the person, let's say the first person be the president, and the second person being vice president, their roles are different if they interchange, right? So order does matter. So let's say roles are different. So order does matter. Right, so now let's do that without permutation. So there are 3 slots. President, vice president, and the Greek consul. There are 20 of them. The first one you can have 20. Any of those 20. The VP, there's 19 left. And for the Greek consul, there are 18 left. So multiply those. That's all we do. That's 68/40. That is if we just use without permutation. For permutation, there are 20 of them, and we only choose for 3 positions. So that how much we have. And of course you can use 20 factorial over 20 minus 3 factorial, or 20 over 17 factorial. Of course you can get the answer. But if you have this calculator, just go ahead and choose permutation of 3. Right, 68/40. Right. Simple enough. Next, you and 15 of your friends, that makes 16 people total. The group needs to do 3 officers, the CEO, operating manager, and the treasurer. So there are 3 roles again, and there are 16 people to choose from. So 16P3 pretty much, right? Yeah. And again, when we choose this, roles are different. Order does matter. So this 16 factorial over 16 minus 3 factorial. So if you do that, well, just use this. Yeah, 3360. Right. If you don't want to do it like that, remember there are 3 different positions. And then you can have 16 for the first part, 15 for the second, and 14 for the next. And multiply all of those 3 numbers. So that's 3360. Right, that's what we have. Right. So the key here is if the roles are different, the order does matter. Right, next. In a lottery game, 40 numbers are put in a bin and 4 choices at random, one at a time. The game, in order to win this game, players need to match all 4 in order in which down round, and how many different winning order are there. Right. So the key here is you have to pick 4 and you have to match all 4 in the order in which down round. So order does matter here, right? Right, and there are 40 numbers. Because order does matter, that permutation. So 40p4. That gives us that much. Right, so that over 2 millions different orders. Right, of course, if you want to, you can also do the slot. The first one can have 40, next one 39, 38, then 37. Yeah. Right, next, permutation rule when objects are alike. Right, now there's some case that not only we have n objects, but some of them are similar. So in that case, what do we have? So for example, here we have the Mississippi. There are a few I's and a few S, right? So let's list. There's 1M. How many I's? 1, 2, 3, 4 I's. How many S? 1, 2, 3, 4. How many P? 2P. Total, that's 11 letters. One M, 4 I's, 4 S, and 2 P's. Right. Now, how many different passwords can be generated using this? So we just scramble off this. Remember, all the S and all the S are the same, all the I's are the same. So it's significantly less than 11 factorial. So the rule says is we start with n factorial and just over factorial of each one of this. Right. I'm just enter exactly as I see it, except for the 1 factorial, which is 1. I don't need to write 1 factorial. Right, so we have 11 factorial over 4 factorial. And then 4 factorial. And then 2. Right. That is 34,650 different passwords can be generated using that. Anyway, so permutation order does matter, and we're going to put we can choose how many objects put in how many places here. Order does matter, so keep that in mind. And with that, we finish section 11.2. As always, thank you for watching, and see you in another video in Math 1332.